this circuit, we want to obtain the energy stored in each of these two capacitors under DC conditions. We know there's DC conditions, direct current conditions, because we only have one independent source here, and it's just 6 milliamps. So it is a DC independent current source. So when we analyze this, we'll still use our voltage current relationships with the capacitor and our energy relationship. So we know that the energy is 1/2 the capacitance times the voltage across the capacitor squared. So we want to find the voltage across capacitor 1, we'll call the 2 millifarad capacitor 1, and we'll call the 4 millifarad capacitor 2. So what we need to do then is to find these two voltages in order to get the energy, because we know the capacitances. So if doing some analysis, that voltage, we can relate it to the current, 1/C, that integral over time of the current to the capacitor, I dt. The current is equal to the capacitance times the rate that the voltage is changing with time. But under DC conditions, the voltage is not changing with time, so the current's equal to 0. So it's difficult to do this integral because we don't know what's happened. We're at the point where the current's equal to 0, but in past history, there must have been a current to get a charge on the capacitor to create a voltage. So this isn't really the approach that we can quite use. So what we need to do, since both these currents are equal to 0 at this time, that's going to happen when we have DC conditions. So if we analyze this circuit with KVLs, for example, if we look at this voltage across the capacitor, VC1, well, we can do that with that's really a Ohm's law there. It says KVL. But that's just equal to our I2 times 2 kiloohms. And why am I saying that's Ohm's law? They're in parallel with each other. So the voltage across this resistor is the same as the voltage across the capacitor. So we've used Ohm's law to say it's equal to I2 times the 2 kiloohms, where I2 is defined as flowing to the right through the 2 kiloohm resistor. So the voltage across the capacitor 2, again, with a KVL, we can say this voltage in this downward direction is equal to negative V5 plus this V4. Well, V5 is negative IC2, or well, V5 is IC2, this downward current times a 5 kiloohm resistor, but that current is 0. So V5 is just equal to 0. And so our V4, which is this I4 here times 4 kiloohms, that's essentially what our VC2 is, right? So that voltage across this capacitor is just the voltage across this 4 kiloohm resistor. And again, this is because the DC conditions that the capacitor looks like an open circuit, so the current's equal to 0. There's no change with time, the current's equal to 0. So if we want to find I4, we can do a KCL here at B. We have I2 flowing in, we have IC2 flowing out, and I4 flowing out. Well, IC2 again is 0, so that makes this I2 equal to this I4. So that's going to make things a little bit easier. So again, what we've done for our analysis then is this KVL, where this VC, this is KVL and Ohm's law, right? Where this VC1 is equal to I2 times 2 kiloohms, and then we did a KVL to find out that our VC2 is I4 times 4 kiloohms. And then we have our KCL, and this is actually, at node B, I think, right? So this should really be at node B, it seems to me, because it's the I2 is equal to IC2, which is down here, plus I4. Yeah, so that should be node B. So that's what we've done. And now when we're looking at our energy, what we really need to find is the I2 and the I4. But what we've shown here, right, is that our I2 is equal to I4. So we really just need that current, and then we can find the energy stored in the capacitors. So again, what we've done so far, we need to add some analysis to that to find I2 and I4. Well, what can we do here? We can do another KCL here. We know this current 6 milliamps flowing into node A. 6 milliamps flowing into node A is equal to the I2 plus IC1, which is 0, plus I3. So our I3 plus I2 has got to be equal to 6 milliamps. We've already done a KCL over here, so we could do a KVL around this loop to get to try to determine our I4. So again, our KCL at A, and then our KVL here, we could just do that KVL in Ohm's law like we would do with our mesh analysis. We get negative 3,000. We're going in the opposite direction of I3 times I3 plus 2,000 times I2 plus 4,000 times I4, but we've shown that I4 is equal to I2. So from there, we can solve for, between these three equations, we can solve that our I2, which is going to be equal to 1/2 of I3, or it's also going to be equal to 1/3 of 6 milliamps. It's going to be equal to 2 milliamps. So then we're able to solve. We can solve for our energy, in capacitor 1 is equal to our, that's a 1, is equal to 1/2. Our C1 is 2 millifarads. And then we have 2 milliamps times 2 kiloohms. So that gives us 4 volts. 4 volts squared. And C2 is 1/2 times 4 millifarad times our 2 times 4 is 16. So that gives us, I'm sorry, 2 times 4 is 8 squaring. So it's our 8 volts. So we could solve for the voltage squared. So this becomes equal to, that's squared. So that's 16 millijoule. Right, 4 squared is 16, 1/2 times 2 is 1, and then we have 64 times 2, so we get 128 millijoules stored in capacitor 2. For that, another way we can do it is if we redraw the circuit. And there's our 6 milliamps, and it's the same way. It's just redrawing the circuit and using less equations. So that's our 3 kiloohms. There's our 2 kiloohms, 2K, and there's our 4K. Now this is a resistor, right? But we'll draw this capacitor as just open, draw this capacitor as open, and then we have our plus or minus VC1, and since that's 0 volts because it's an open circuit, there's our plus or minus VC2. So we have to just make sure that we can see that, and then we can see, then we can see that we have this current. We'll call it I2. Since this is 0, this is also I2, and then we can still call that I3. We can just do a current division, but our VC1 is equal to I2 times 2 kiloohms, and our VC2 is equal to I2 times 4 kiloohms. So now we just need to find I2. We can find our I2 with a current division. I2 is equal to the 6 milliamps times, since we'll do 1 over 6K, divided by 1 over 6K plus 1 over 3K, and those are ohms, or equal to 6 milliamps times 3 over 6 plus 3. So it's our 1/3 of 6 milliamps, which is what we found before. 1/3 of 6 milliamps is equal to 2 milliamps. So then we plug this up in here, and that becomes equal to 4 volts, and that becomes equal to 8 volts. And once we have the voltage, we can get that our omega 1 is 1/2 VC1 squared. We forgot our C, so we'll do C over 2, and C1 over 2, and energy 2 is C2 over 2 times our C2 squared. But so here what we did, instead of going through all those KVLs and that analysis to show that that's zero, we jumped right to the conclusion that at DC our capacitors are open circuits, and we drew them as open circuits in the diagram. The thing that's sometimes more difficult to notice is that this voltage across the 4 kilo ohm resistor is the voltage across this this capacitor, because this voltage is zero. All right, that's it for this video.